Uh, Good afternoon, everyone. Welcome to the H3D Foundation webinar series. My name is Shruti Singh, and our today's speakers are Dr. Vinayak Singh and Dr. Godwin Dziwornu. They represent Holistic Drug Development and Discovery Center, which is H3D. H3D operates within UCT's world-class translational medicine research environment. Dr. Singh is involved in molecular biochemistry, genomics, and metabolomics, and his main interest is to deconvolute mechanisms of action of potential compounds to fulfill a broad and acute interest in the discovery of new innovative drugs. Dr. Dziwornu has expertise in organic chemistry, medicinal chemistry, and natural products, and he is involved in designing novel chemical series for exploration as anti-infective agents towards the drug discovery venture. Before we start with the talk, I would like to let you all know that we will have a Q&A session after the talk. So the questions can be posted in the chat or kept for the end of the talk. So today's topic is the implication of Mycobacterium tuberculosis-mediated metabolism of targeted xenobiotics. And now I would like to request the speakers to enlighten us with their work. Over to you, Dr. Singh and Dr. Dziwornu.
Thank you, Shruti, for the kind introduction. And Godwin is very happy that you pronounced his surname correctly. Can you please confirm that you can see the slides in a slideshow mode?
Yes, we can see your slides.
Great. Thank you. Good afternoon, everyone. So today we will take you through some new concepts on related to Mycobacterium tuberculosis and basically highlighting some of the Mtb-mediated metabolism of targeted xenobiotics. So let's start. So I don't think that you're not aware of TB, especially if you are attending this webinar from South Africa or any developing countries. But this is also a big problem now in developed countries as well. So briefly, if you want to really understand what the TB is, it is caused by a bacteria that the name is Mycobacterium tuberculosis. We call it MTB in short. And currently, TB is the world's leading cause of death from an infectious disease. Yes, that's true. It's no longer COVID-19 anymore. And this is a leading example of the growing problem of antimicrobial drug resistance. And if you look at the profile of antimicrobial drug resistant death, TB, at least 1 out of 3 deaths related to AMR is because of TB disease. So in the current world, in the globalized world, anyone can be at the risk from TB. And ideally, as it happens with most of the infectious diseases, we could prevent TB with a vaccine, but currently we only rely on the BCG, and that is generally effective in the early life stages and up to I believe 6 years of age. So definitely there are various groups who are looking and they're investigating a way to find the best vaccine which can be applicable to adults as well. So currently chemotherapy remains the main option to deal with active TB. So this slide gives you a general idea of the history of drug discovery and development. And if you Shruti, can you confirm if you can see my cursor as well?
No. Can you move your cursor, please?
Now?
Yes, yes.
Okay, great. Thank you. So I just want to bring your attention to this era before 1943. And, if you look back at the history, we have some documented, literature which is available and that only goes up to 1800s. So if you look at this, this is very interesting. And if you're not really, involved in drug discovery and development of TB or any other infectious diseases, this is fascinating to know actually that before 1943, before the invention of streptomycin, if you come across TB disease, we were relying on good nutrition and rest. Experiments with inhaled iodine and gold compounds were made, but obviously there is no solid evidence how effective these were. But as you see, after the invention of streptomycin in 1943, there was a slew of other drugs which scientists have found up to 1963 that involves para-aminosalicylic acid, isoniazid, pyrazinamide, cycloserine, kanamycin, ethanamide, capreomycin, and ethambutol as well. And the interesting thing which I want to highlight from this slide is that if you focus on streptomycin, it took only 5 years for bacteria to develop resistance against streptomycin. And you see that's you can see the machinery of MTB, how clever or smart it is if you want to put it in that respect. And as you discover more drugs, the bacteria, was always equipped with alternative modes of developing the resistance. And that's where in around 1957 there was emergence of multi-drug resistant. And but obviously with the invention of rifampicin, mostly world clinicians, they found a cure for TB. And after that it was kind of, we call it innovation gap, and because there was no such need, there was treatment was available, and that can take up to 9 months of treatment, right? There was not a lot of multi-drug resistance strains available in that time. But in during late 80s and 90s, there was a kind of, epidemics, or not epidemics, kind of, a burst of drug-resistant strains emerged, and that again, forces scientists to really look for new anti-TB drugs, and that's where, we came up with improved rifampicin, that is rifampicin, bedaquiline, delamanid, and pretomanid. But again, so if you come to this slide, this is the current scenario, how the TB drug pipeline looks like. And this data is from late November 2022. And what you can see, actually, there are a number of compounds which are in pipeline at various phases of drug discovery. So, and this is a busy slide. Don't worry, there are links on the slide if you want to go in detail. There is a lot of information available on this new TB drugs website. If you have never visited, I would highly recommend to visit this, and you will get a lot of information, and it's very good information. It's up-to-date information, which may not be available on various publications, but the information is available on that website. And that involves from the discovery, preclinical development, clinical development, and at various, because now there are new regimens are going on, which we call it new combination regimens, and you can get the up-to-date information on that website as well. But what I want to highlight from this slide, that for us, like the people who are basically engaged in the early drug discovery phase or development, for us there is a this lead optimization or early drug discovery phase is the area of need and opportunity, and that's where our main focus is. Okay, so let's shift the focus to the related concern and to the topic of this talk, actually, and why we want to talk about the MTB-mediated metabolism, and what is the concern actually. So as you know, so the first bullet, that's in green because that's very good for us. A couple of anti-TB drugs actually get activated via metabolism inside MTB, and you can call this in a very simpler way. We call it prodrugs, right? So prodrugs, once inside the MTB, they get activated, and that's how bacteria are being killed, right? And Godwin will, define these terms which we are, bringing uh, during this talk later on. And then the next bullet point is in red, actually, and it says a number of potential compounds get deactivated inside MTB. And that is the major concern. And that's what we want to highlight during in this talk actually. So what happens, the compound really look very good. It has all the drug-like properties. We get activities, but what happens, somehow it gets deactivated once it is inside MTB cell, right? And you don't want that if you want to develop that compound into a drug, right? The third point, actually, this is more like, not a concern, but it's a reason, and we need more, research in this area, that owing to the complexity of the disease pathophysiology, means TB is a complex disease. The metabolic target and inhibitor pair do not always translate into a successful outcome, and the literature is full of those, reports or evidence. Okay, so let's come to the topic. What is drug metabolism? So I'm not the expert on this, but if you want, you can. I've just put the links here, and these are the links belongs to two excellent talks which were given on this same platform on STD webinar by my two colleagues, Matthew and Lizel. You can go through those talks and you can learn in detail about ADME and PK. But in briefly, what this figure is highlighting, that after drug ingestion, right, there are four main uh, phenomena which happens to the drug. That is absorption, right, distribution, metabolism, and excretion, right? And if you really want to see what happens, so in the figure on your left side, you see there is a drug going in, and then this is the gut wall, basically intestinal wall and everything. This is, we call it first pass metabolism. Then the drug passes through. This is the liver, and this is the main, you can say, metabolic center, metabolism center, actually, but not only for the drugs, but for many other things as well. And then here the drugs will phase, and sorry, so please do not confuse with drugs. These are therapeutic compound or therapeutic drugs, okay, not the drugs, okay. So these are the, like hepatic metabolism, and then obviously finally it goes to extrahepatic metabolism and bioavailability. And if you want to really understand what the bioavailability is, you can define it like bioavailability refers to the extent and rate at which the active moiety or species of drug or metabolite enters systematic circulation and thereby accessing the site of action. And in case of TB, it's quite complex because the MTB resides inside lung, then, various dead cells, or, like protective layer of calcium and so on, like granuloma. So that's, that's the topic on itself. Anyway, so I will hand over to Godwin, who will take you through all the hardcore chemistry, which he is the expert, and will explain you about what the metabolic reactions are and what is the role of MTB.
Okay, thank you so much, Vin, and welcome everyone. So as Vin has laid a good foundation, I'll just top it up with some ice cream, let's say, so to speak. So going straight into it, our bodies, or we usually basically have two phases of metabolism. So what we would call the phase one metabolism and the phase two metabolism. So here you find examples of phase one metabolism, and the idea here, or the primary objective, if I should say, of the body in its way of keeping xenobiotics or exotic materials out, would be first to polarize it or make it very polar so that it can easily get out, usually or mostly through excretion. And in phase one metabolism, you will find that you have the addition of polar groups, if I should put it that way, or water solubilizing groups, to form metabolites that tend to be water soluble and polar, and so they are easily excreted. It is also worth mentioning that some of these metabolites become substrates for phase two metabolism, and that I would explain, or I would briefly describe in the next slide. But what is worth mentioning, I think, is this point here, the fact that the metabolism, whether phase one metabolism of a drug let's say, could yield a metabolite that is potentiated, meaning that it becomes more active. The metabolite may retain a similar activity to the parent compound or the parent drug, or the metabolite would be completely deactivated. And again, we will see examples in the slides that follow. So this is quite important. And just to go through briefly on some examples of drugs that we are very familiar with and how they are metabolized at the phase 1 level. So we all will be familiar with ibuprofen, and here you would see going through aliphatic hydroxylation. So you have the hydroxyl group being incorporated at this tertiary carbon center, making it again more polar and so easy to excrete. Our bodies also have mechanisms to do N-dealkylation. And again, you see you have a methyl group or an alkyl group, and then it releases the free nitrogen, making it more polar. You can have an oxidation also occurring on amines, free amines, as is exemplified in this drug here. Aspirin, which we are very familiar with, is metabolized by hydrolysis to salicylic acid by deacetylation of the acetyl group here, as you will find on the cursor. And again, it's nature, and so you cannot really predict where things can just happen. Here we find hydroxylation occurring on the aliphatic center. It also has mechanisms to hydrolyze an aromatic ring. And here you see oxidative deamination. You can have XS oxidation, or you can have oxidation again, an example of oxidation of the nitrogen of a nitrogen center. So these are all abilities or capabilities of our bodies, of machinery in our bodies, to keep the body in the state, in let's say, in a constant state. So bringing a new, an exotic, a foreign body, it wants to get rid of it. It always wants to maintain what is known to it naturally. And so that's why we have these mechanisms in place in the body. But as I did mention earlier, they could be beneficial even to us. So depending on us as drug discoverers, if I should put it that way, we shouldn't see these processes as just being on the bad side. We can take advantage of them to our benefit, to either activate a drug, then we don't care. I mean, if the activity is unchanged, or when it is deactivated, then we have to go back to the lab and try and fix that problem. And that is something that I am very sure the chemists and the biologists on this platform are very familiar with. In phase 2 metabolism, as I did mention, the phase 1 metabolism, the substrate or the metabolite tend to serve as substrates themselves. And here what you have happening is that you have these endogenous hydrophilic groups that tend to be conjugated to the hydroxyl groups, the amine groups, or the polar groups that are exposed in phase 1. And this makes the compounds even more inactive, easy to excrete, very hydrophilic, and then they just washed off largely through excretion in urine. So here you can have sulfation going on, you can have hydroxylation going on. Again, we've seen this before. And then, so this is an example of a combination of phase 1 and phase 2 metabolism, where hydroxylation exposes or introduces a hydroxyl group, and then glucuronidation introduces this glucuronide, which is, as you can see, very hydrophilic and so easily washed off. This is another good example. You have phase 1 oxidation going on, and then this produces a very reactive metabolite, a reactive metabolite. And so you can have proteins with thiols getting conjugated. And because of protein hydrophilic, they are easily deactivated or knocked off the system. Glutathione also serves a similar purpose, where also having a thiol center could also easily get conjugated to these reactive metabolites, these quinone-imine reactive metabolites, and so are shut out. For us in H3D, very much interested in malaria, amodiaquine is a good example of this kind of metabolism, where the phenol side chain, the phenolic manic base side chain, is taken into the quinone-imine and then easily washed off with glutathione conjugation as a metabolic pathway. So this, having said this has to do with just what happens in our bodies, the intrinsic processes and capabilities in our bodies to maintain a balance with our systems. Now let's delve into MTB, which is what we want to really focus on here. So what it's worth highlighting is that drug metabolism is not just restricted to the liver. I mean, the intestinal tract can metabolize drugs. The gut and the lung biomes, microbiomes could also, we can have metabolism happening in blood. So it happens all over the body. But an extra addition when it comes to MTB is where the parasite itself also joins in this battle of getting things out of the system. And that is where it becomes interesting, or it becomes an additional work, because while as chemists we could solve the metabolism with chemistry work, but then MTB introduces its own. So MTB has remodeled its metabolism to either biotransform a drug to an active compound, which we would call a prodrug that would be full to the MTB, and then where it inactivates the drug, and so we want to call it, or that is what we are calling here, friend. So just to explain the concept very well, because we are going to see friend and foe very much in the next slide. Friend and foe is specific, or we are specific to the bacteria. So when we say foe, we mean it is foe to the bacteria. So MTB would metabolize a drug and then make it more active. That in that case, the drug is, say, a prodrug, and so it activates the drug, in which case the metabolite, which is more active, now becomes an enemy to the MTB, or a foe. In the other instance, if MTB metabolizes a drug to the metabolite, which is inactive or loses potency with respect to the parent drug, then it is a friend to the bacteria, and so the bacteria can thrive or survive. So those are the two concepts we want to present here. So nothing about us. We are talking with respect to whether MTB is enjoying its metabolism or it's not enjoying its metabolism, so to speak. Now, in the next slides, we want to talk about examples of biotransformation mechanisms that is within the capabilities of MTB. Here we will show some enzymes and some chemical transformations that happen with real examples of drugs in the literature. One thing that is worth mentioning is that some of these drugs, we will not try and delve into the mechanism of action or resistance of these. I think that can be the subject of another talk. But it is worth knowing or noting that these metabolisms can give an idea of the mechanism of action or of resistance of the drug or the drug candidates that is in question, so to speak. Brief examples. We are very familiar with these drugs, TB drugs, anti-TB drugs. In fact, isoniazid, pyrazinamide, ethionamide, and britomamide are all prodrugs. And here we see Mtb-mediated metabolism. Isoniazid undergoes oxidation to form this anion that is, in fact, the active drug. Pyrazinamide goes to the pyrazinoic acid, and then you have all these other. So here is an example of the description of food, where the drug is a prodrug, is activated to a metabolite that is detrimental to the bacteria. And so these then are, in fact, the active metabolites of these drugs, of the isoniazid pyrazinamide, or these prodrugs as we know. On the other hand, kanamycin and its group of mycins are aminoglycosides, and these are this is an example within the context of trend, because then again, enzymes available to MTB, you can have acetylation of the amine. So you can have either the monoacetylation or the diacetylation to make it an inactive metabolite. And so here is a description of the concept of friend. So a very active compound gets metabolized by acetylation, and then you get an inactive one. And then you can also have phosphorylation happening at this C3 hydroxyl group to form the kanamycin 3 phosphate, and that is also inactivated. So here we see common drugs that we are familiar with within the space of TB, drugs that are known in the clinics, and how Mtb-mediated metabolism plays a key role in how these drugs tend to function. Now, I've done this already. I think by now you understand the concept, but just to put the speech in text. So for, we mean an inactive compound, a drug, to an active metabolite, and that we will call an activation. So it is inactive, it's a prodrug, MTB metabolizes it, so you can have activation happening from MTB metabolism. You can have bioactivation happening, and that is an active compound becomes more active, a more active metabolite. Now you can have the active compound give an equally active metabolite. Now that is fine. All these three cases will be good. I mean, they are fine. An active compound to an active metabolite with an entirely different pharmacological activity. Now that is also there in the literature. Examples are very, very much known in the literature. Another thing what we would move on to is the friend, where you get whether inactivation or complete detoxification of the drug. So if we have these concepts in mind, then we can really delve into some of the examples to really see what the capabilities of MTB are. And I think that the key thing here, the message that we want to put across, especially to chemists or to my chemist colleagues, is that understanding these processes can pre-inform us, if I can use that term, as to what groups we have in the drugs that we are making, especially if we want to target TB, and what we should be doing or what we should be thinking about when we want to come up with a drug. We may have a drug very potent with a nitro group, but we must be sure to know that MTB has a propensity to reduce nitro groups to an amine or completely remove the nitro group. And that is what we want to highlight in this talk. Okay, so enough of this slide. If I were just zooming into some good examples that we have here. So here is an example of a triaza-coumarin compound. And here you see MTB reduces this alpha-beta unsaturated system here to give this aliphat. It reduces it to this group, and then by spontaneous hydrolysis of the ester gives the free carboxylic acid. Now here it is within the context of full. So MTB undertakes reduction to give this compound 41, which is in fact the active metabolite here. Now in this natural product, nitrofuranol calanolate 42 and 43, you see another example of a reduction, but this time you have reduction of the nitro groups to the free amine as an example. Here we have another reduction going on, but this time it's not just the reduction of the nitro group to the free amine, but you have cleavage of this 5-membered ring completely. And again, another reduction. So again, examples A, B, C, and D highlights something key, MTB does not have only one linear way of reducing groups. It can undergo reduction, and all these are capabilities that it can use. Then you can see that there are 4 different enzymes involved in just reduction of coumarin or an alpha beta group, a nitro group, and then other groups, as you would see. Now here you can have oxidation of the thiol going on. These examples, so these 3 compounds here are compounds that are involved in the tryptophan biosynthetic pathway. They are inhibitors of the tryptophan biosynthetic pathway. This example here, G, is also targets the tryptophan biosynthetic pathway. However, how it does that, so it is a product on its own. It first undergoes amide hydrolysis to form the free amine. Now that serves as a substrate for metabolite incorporation by another enzyme to form this metabolite for amino L-tryptophan that is incorporated in the tryptophan biosynthetic pathway, and that is toxic to MTB. This compound here, these oxime carbamate, are from, in fact, is from our own lab in H3D, where we have demonstrated that it serves as a prodrug, where hydrolysis in MTB of this carbamate group gives the hydroxylamine, which is in fact the active metabolite. So these are examples, some more examples just to touch on quickly. Fusidic acid is a natural product. So fusidic acid compound 59 is a natural product based antibiotic. Prof. Kelly Chibale's academic group has done extensive work on this compound. And fusidic acid is very active in vitro against MTB. The activity is somewhere in the low nanomolar, less than 2 nanomolar there, 200 nanomolar thereabout. However, fusidic acid is metabolized to the epifusidic acid in rodents. And epifusidic acid, just by epimerization, gives the inactive metabolite, the 3-epifusidic acid, which is inactive, as I said, it happens in rodents. And this has stalled the further in vivo proof of concept studies in rodents because of the propensity to form the 3-epi, which is inactive in rodents, as I've said. Now, the strategy here was to make a prodrug by esterifying fusidic acid so that in ester hydrolysis, whether in rodents or in MTB, because MTB is able to release this, we can bypass or save some time in the metabolism to 3-epifusidic acid. We can make enough of fusidic acid, the parent drug, in MTB to effect the change or to see some rodent activity. Now, MTB is able to do this, as we've said. These are some good examples where when we made the silicate, this is the silicate ester. This is, in fact, very stable even in rodents and also in MTB. Quite intriguing to note that while MTB can do the C3 hydrolysis, ester hydrolysis, it cannot do the C21 hydrolysis of this phenyl ester in compound 62. Again, something that we triggers something in our minds. It's not linear. It is based on enzymes and whether the compound or the drug as a substrate fits well into the enzyme in order to effect the hydrolysis that we would observe. So this is quite, these are examples. Let me mention again one other metabolism that goes on in MTB is the metabolism of fusidic acid to the 3-keto fusidic acid. And that is just reduction at the C3 position here to the keto group. And that is equipotent to fusidic acid in MTB. So these are well established. We've published, the data has been published over the past few years. So we all know para-aminosalicylic acid is also another example of 4. And here you will find N-alkylation. This is just one metabolite. It's active as the parent, but then double alkylation gives an inactive metabolite. See, and these two can incorporate into the folate metabolism pathway and effect a change, or can give us the kind of activity we want. But again, the NN-dimethyl PAS is inactive. So these are examples just to, again, trigger in our minds what MTB as a parasite or as a microbe is capable of doing, so that when we are making our compounds, when we are thinking of what getting a drug on the market, we should be aware of what is happening. And again, all these examples give an idea, or could give an idea of what is capable, the resistance mechanisms that we would see. And again, as I said, this talk is not meant for that, and that can be the subject of another talk. So lastly, I would just finish off with this slide here on examples of friend. So here we have this group, and we have oxidation happening at this center here, and this makes it very liable to cleavage, and so you form inactive groups. So 70 is active, however, it produces inactive metabolites through oxidation in MTB. And while nitro reduction could give activation in one sense for when we were dealing with 4, as we had shown, here nitro reduction could give a friend situation in another sense. It is still MTB is doing its own thing as to what happens to the drug friend or foe. It doesn't seem to really worry about that. So I'll finish off with this last slide and then move it, this last example, and then move it back to give it back to Vin to complete the talk. But here again, we can have hydroxylation happening. We can have hydroxylation of the phenyl group, as we have seen in these 3 examples here. Or we can have N-alkylation also taking place. And you can have alkylation, for example, here in metabolite C. And again, I think I just want to hammer the same point again. These are studies that give us something into what MTB is capable of doing, so that in a drug discovery venture, we should look beyond the phase 1 and phase 2 metabolism as we would have it, and think also at the back of our mind into what MTB is capable of doing. And these are just a few examples to highlight these points. Thank you. I would move over to Vin now. I'll give it over to Vin to complete that.
Thank you, Godwin. You have very excellent, examples you've discussed. I hope everybody enjoyed this. So next I will move on to basically, the issues which we have discussed so far. And for us, for the, the researchers who are involved in drug discovery, for us, our main issue is to deal with the friendly biotransformation reactions and how to deal this. So if you have attended the previous STD presentations, you may know, or you may be familiar with this type of cascade, which we generally use in our project. And this is just basically, a kind of, flow diagram where you could see what we do from, starting from compound libraries and to end with the endpoint that could be, lead optimization, or, moving the sample, moving the drugs to various phases of the clinical pipeline. But here, what I want to bring your attention to, the highlighted, the green boxes and the blue boxes. And this is what we propose. Like if you, face the hurdles of friendly biotransformation reactions associated with a particular series or compound or any particular uh, drug of interest, I think the best would be, to identify those friendly biotransformation reactions of MTB against the compound of interest would be, the assessing MTB-mediated biotransformation reactions, at the first phase. The moment you identify primary hits, just put all those hits through the assessment. And that would be like, it can save our time and investment. And how we can do that? So for that, we can, perform a slew of in vitro assays. That could be, various media conditions. That's where we want to test the stability of the compound itself in media, and in the MTB itself, whether MTB has any, it's biotransformation activity against that particular compound in the culture media itself. And then in the ex vivo, ex vivo means you basically treat the compound or expose the compound to intracellular MTB, where the MTB resides in the human cell line or murine cell lines, and then you try to find out whether your compound is stable or not. And based on the outcome, you can always go and subsequently identify the metabolic ID or fingerprints. And based on that knowledge, if there is any issue, you try to sit down and see if you can solve that risk early on. And obviously, another thing could be, creating or constructing a variety of MTB recombinant strains where you overexpress a number of metabolic enzymes, which Godwin has highlighted in his slides, and just create those overexpressors and try to profile all the hits against those overexpressors to basically verify or to get a sense whether there is a risk associated or not. And this is the first phase, and this is basically related to MTB mediated. But obviously, you can also focus on assessing the host mediated biotransformation, and I will highlight in next couple of slides why we are talking about that. And this could be by performing the detailed pharmacodynamics and pharmacokinetic studies. And this is, I think, moving forward, this is very crucial, uh, especially when we know that a number of compounds are failing in making to the next steps. Okay, so let's shift a little bit focus on role of gut microbiota in drug metabolism, as Godwin has highlighted in one of the slides where you have seen the lung structure and everything, and what could be the factors where the metabolism can happen. So the gut microbiome actually can directly influence anti-TB drugs, or for example any other drugs as well, by metabolizing them into active metabolites, inactive metabolites, or toxic metabolites. And obviously, on the other hand, the gut microbiome actually can also influence the immune pathways, or pathways resulting in the drug absorption, for example, or bioaccumulation. This is a very, very new field actually, and the recent publications have come up in very prestigious journals actually, where they have really highlighted the concept of bioaccumulation. And these are very crucial because these will determine what would be the drug concentration that is entering into the systematic circulation, or the bioavailability of anti-TB drugs, and that could be affected by drug absorption or bioaccumulation that are mediated by the metabolism of the gut microbiome. And these, like, if you put it together, there is a new uh, branch of actually science is coming up, and we call it microbiomics, and that is very interesting actually. And I think that would be very interesting in terms of when we analyze the TB drugs in the context of microbiomics. So to this, in this line, I just want to I have only 2 slides to give you a snippet of our work, and briefly sharing, basically I'm not going to show the data, what we have. I would say rather preliminary data, but I just want to share what the hypothesis is. And this is not like in terms of gut microbiome, but on a different spectrum. Here we want to analyze the MTB specific metabolism, right? So the hypothesis, what we want to address is that MTB metabolizes antiretroviral drugs in patients with TB and HIV comorbidity that might require adjusted doses of antiretrovirals. And the same hypothesis actually we can apply for co-administered drugs as well, right? So the proof of concept could be the clearance of anti-HIV drugs by MTB measure can be measured in vitro, followed with ex vivo and in vivo. And the challenges which we faced that there are over 30 antiretroviral drugs are available. And obviously there are many co-administered drugs. And there is no clinical evidence. So this is completely, uh, new way of thinking. Uh, and there is no literature available, obviously. So the workflow which we are trying to optimize for that, and obviously this is in collaboration with Arcelia. You may remember Miguel and Kema, who have presented and discussed their approaches in one of the STD Foundation webinars. So what we want to do, we want to just filter out or select antiretrovirals based on AI or machine learning models, and this we are trying to combine with PBPK. This is basically physiologically based pharmacokinetics modeling, and this considers various physiological parameters like fraction in the liver, penetration to lesions, we call it KCM, macrophages, lipid layer permeation, MTB cell wall permeation, and then how it interacts with enzymes and or bioaccumulation. So this is a complex the modeling thing, but we are trying to address, and let's see. I hope that one day we will share those results in this forum. Time, right? Okay. So finally, the take home message, what you can really uh, get it from this presentation, and at least what we have got from this research, that the mechanism underpinning intrabacterial biotransformation are useful in discovering next generation antituberculosis that are well suited to treat TB. We also need to collect our some focus towards identifying the metabolic soft spots early on. That would be great, and that's what we have proposed in the cascade. And obviously the use of machine learning tools, which many researchers are already doing in other drug other disease areas, which I think we can also utilize in the TB field. For example, predicting phase 1 and phase 2 drug metabolism. And there are softwares available like Metasite, Metaprint 2G, AdMeT, AdMeT Predictor, and RS Web Predictor. And some of them are free to use. Some of them, like, you need to buy the license, but obviously based on your need, uh, uh, I would highly recommend to at least learn about them and utilize them in your research. And finally, understanding the metabolic pathways, because as Godwin has mentioned, we know about these examples which he has shared. These are not all the examples. There are many more examples which are available, not only in TB but in other disease areas. And most of the things actually we don't know. So as we move along in the drug discovery phase, or mode of resistance or mode of action experiments, we always learn those. So I think this is a continuous process of understanding metabolic pathways, and whatever information we get in mode of resistance studies, we should not just ignore them, because most of the time in the drug discovery phase, that is the dead end when we do not have the answers. But I think we should utilize that information going forward. And finally, so whatever we presented, some of these concepts are recently published. This is in online available, and if you use the link below, which is rdcu.pe, I would pause here actually so that you can note it down, this link. If you use this link, you can open or access this article free of cost. Okay, otherwise there are about, if you want to access, there are like around $40 fee. So I hope you have noted it. And before I end my presentation, I would like to acknowledge and And obviously, it's a Professor Ken Chivale and number of colleagues for all the valuable discussions. Within STD, beyond STD, it's a lot of learning during this, writing and collecting, and it's a continuous learning. So we are very, very thankful to all the discussions. Uh, and obviously, we generally, do not give credit to all the failed compounds and the series and the interesting metabolic processes, which people generally, or for variety of reasons, we couldn't publish. But I think there are many learnings out there to build a pipeline or database where we can really, mine those for our use. And finally, the challenges of the drug discovery and development. And if you're part of drug discovery and development, it's not new for us, but for those who are not really involved in that, there are numerous challenges. Okay, but that's what we enjoy, right? And finally, to the funders, Gates Foundation, MRC, and NRF, there are many more funders, but we are just highlighting a few.